Good afternoon. We're going to continue talking about boundary layers, turbulent and laminar flow today. So I want to draw the boundary layer profiles up here again. So these are velocity, horizontal versus the height above the surface. And a turbulent boundary layer looks like that. A laminar boundary layer looks like that, where the turbulent has a high slope, dV by dy. And that's the slope at the surface. And then laminar has a lower slope, dV by dy. And the key here is dotted is turbulent, solid is laminar. And the turbulent boundary layer has a larger thickness compared to the laminar that is thinner. Because the shear stress at the wall is proportional to that slope, dV by dy, it means that the drag for turbulent flow is greater than the drag for laminar, because the slope of the turbulent flow is higher, and the shear stress creates the drag. And your book shows you a couple airfoils that have laminar flow. And airplanes were designed for several years to have this kind of laminar flow. And you can read this section on page 234 through 236. That talks about the airfoils and the laminar flow. So we want to look at predicting the thickness of the boundary layer as the flow goes down a flat plate. I'm going to give you some experimental or empirical formulas that help us predict the thickness of the boundary layer, the shear stress at the wall, the total drag of the flat plate, and things like that. So here's our flow. Here's our flat plate. It's going to have a total length of L. And we measure distance down the plate versus X. And the boundary layer thickness increases or changes as you go down the X direction. So from experiment and theory, a laminar boundary layer, the thickness can be predicted with this formula. And for a turbulent boundary layer, you have this formula where that Reynolds number, REX, is calculated as the density times the velocity times the distance x divided by the viscosity. So at any distance x down the flat plate, this formula gives you that boundary layer thickness. All right, so that's the boundary layer thickness. How about the friction due to this boundary layer? So there's another set of experimental formulas for laminar and turbulent. So first we have to define what's this skin friction. And the formulas are given for what's called a local skin friction coefficient. And it's called C for coefficient, F for friction, and it's the friction at a certain location X. So we're just measuring the friction at that point, and it's defined to be that shear stress at the wall. So this is force per unit area, so it's like a pressure. And then you divide that by 1/2 rho v infinity squared. If you remember, this is what we called Q infinity, or the dynamic pressure. So that's a measure of how much energy there is in the flow. And V infinity comes from this flow out here in front of the plate. Same deal with rho infinity. So those are all properties of the flow coming into the plate. And the reason that we divide the shear stress at a certain location by this number is because people have found out that if you crank up the velocity of the flow, then the shear stress changes according to the velocity squared. And if you increase the density, there's more molecules to hit the surface, and so the shear stress goes up linearly with the density, proportional to the density. So by dividing through by that, we can take out that relationship or that dependency, and we can come up with formulas for this that are good for any density and any velocity. Because if you want to calculate the shear stress, the tau, you take the formula, you calculate this, and then you multiply by whatever your velocity and density are to get the answer that you need. So I can give you a formula that's good for any velocity that's low speed, all the way from 0 up to 225 miles per hour, and for a lot of different ranges of density, and you just have one formula for all those velocities and densities. All right, so the formulas that you need, and by the way, these are the formulas that you're going to be using in the homework that you're working on. You need the boundary layer thickness formulas. And then here's formulas for what's called the local, and the reason it's called local is because it depends upon which position X you are down the plate, so it changes with position. So let's see, for laminar, the skin friction formula for the coefficient, calculate from this. And again, you have to calculate that Reynolds number. And then for turbulent, there's the formula for that. So again, you take your X position, calculate the Reynolds number, calculate this number here, and then for the given velocity and density, you multiply by this to get the total skin friction. All right, what if we want the total drag on the plate? Well, what we have to do is add up all of the shear stresses, which is force per unit area, multiply by the area to get the total drag. So obviously how long the plate is, how wide the plate is. So the formulas I'm going to give you next are for the total skin friction. Oh, did I erase that too fast? Did you guys get that down? Everybody good? Good? You need it? So what? Better put that back up, huh? I'll move down here. So this is laminar. I'll move down here. So tau sub wall is force per unit area. And so if we want to calculate the total drag, due to the skin friction, we simply add up all the tau sub walls multiplied by the area at that location. And we do this for the whole area, so that's just an integration, because tau changes with position. So we take the tau times its little area, next area, all of the different taus, and add them up, and that's just integration. And of course, we're going to do the same thing. We're going to create the total coefficient, the total skin friction coefficient, because this drag is going to depend upon how fast the flow is and what the density is, as well as the area. So we're going to take out those effects. We're going to divide the drag per unit area, and then divide by the 1/2 rho v squared. So the formulas make it easy. You have a formula for C sub f. You calculate that for your plate. You multiply by the area, because the bigger the area is, the more drag you're going to get. And you multiply by 1/2 rho v squared, because the faster the flow is going, the more drag you get. So again, we're going to have formulas just like these, but it's going to be for the total drag of the plate. So this is the total skin friction coefficient for laminar. For turbulent. And on all these formulas over here, we had RE subscript X, because that was at location X. REL just means you replace X in the formula with L, because it's for the total length, not at any specific position. So REL is rho infinity, V infinity, and then you got an L instead of an X. And so that's where the length of the plate comes in. So again, you want to get your total drag of the plate. You go over here, you know the length of the plate, you calculate Reynolds number, plug it into the formula for turbulent, get C sub f, plug that number in here. To get the total drag, you have to multiply by the area of the plate and by how fast the flow is and what the density is. So you'll get D sub f is C sub f times Q times S to get your total drag. All right, so we've been talking about two different kinds of flow, laminar and turbulent. So the question might be, well, where do you see these two different kinds of flow? It turns out that on a flat plate or an airfoil, you get both. So let's look at the flow going over our flat plate again. If the plate is long enough, you initially get a laminar boundary layer. Nice, smooth flow, not very much mixing. And that at a certain point, the flow gets disturbed enough by the roughness that you get what's called transition. And you get a turbulent boundary layer after that. And that transition point, the critical distance where that transition occurs, depends on the Reynolds number of the flow. So we calculate what's called the critical Reynolds number. And where that happens depends upon factors that you might suspect. The surface roughness, obviously that's a factor because the surface roughness is what causes the boundary layer to begin with. So a rougher surface will actually cause the boundary layer to transition faster. Also, Mach number will have an effect. And any pressure changes. As how is the pressure changing? Now on a flat plate, you get a uniform pressure, but on airfoils, which we're going to talk about in a minute, the pressure is changing as the flow goes over the airfoil. So on an aircraft wing, you will find a point on top of it where the boundary layer changes from laminar to turbulent. And so that's why, talking earlier, they just tried to design aircraft wings that maintain laminar flow over the entire wing because it has less drag. So they thought that was good. Makes sense, right? Less drag, less fuel required. But it turns out there's another effect that can, the laminar flow can actually cause problems with this secondary effect, and it's called flow separation or stall, which you've heard about, right? Stall is where the wing loses lift, and if you stall badly, you fall out of the sky. Well, it turns out that laminar boundary layers stall easier than turbulent boundary layers. So it's kind of a trade-off. Laminar has less drag, but it stalls easier. Turbulent has more drag, but it tends to delay or prevent stall. So I want to explain that next. All right, so this is going to be, I don't know, not a real technical explanation, but you have to pay attention to the details. So take a deep breath. Get ready to concentrate for 4.5 minutes, maybe 5, but I think we'll do it in 4.5. All right, so the first thing is to draw an airfoil that's producing lift, or a wing. Which means that the pressure on the top is usually less than, on average, the pressure on the bottom, and it's that pressure difference that creates the net force. So you have higher pressure on the bottom, lower pressure on the top, you get lift out of it. So when this happens, you've got flow out here in front that has uniform velocity and pressure and density. But as the flow encounters the airfoil, one of the streamlines goes around the bottom, and here you have the higher pressure. And another streamline goes around here, and as it goes around the top, the pressure is going down. So you get a low pressure region on the top, because we're getting lift. And then this flow comes around the end, and eventually it's going to go back to the uniform pressure out in the atmosphere. So that means that this pressure, as it's coming around this way, the pressure now is going back up, and you get a higher pressure than the low pressure here. It's still maybe lower than down here because you're getting net lift, but the key feature is that you're in this region here where the pressure is increasing. So far, so good. Flow goes around the bottom, pressure goes up, flow goes around the top, it gets low, and then it has to come back to normal pressure as you get down the edge of the airfoil. Okay, so let's draw a boundary layer profile of the boundary layer right here where this pressure is increasing. All right, so I'm going to take a snapshot of what the flow looks like really near the surface inside that boundary layer. And it looks like this. And remember that the pressure is going up. So as this thing moves down the flow, we have higher pressure on this side of that region. So it's pushing on this. And then we have low pressure that it's moving from. So it's moving from a region of low pressure to a region of high pressure, which means the velocity is going down, right? Bernoulli's law, Newton's law. If you have a net force backward, higher pressure over here, lower pressure over here, net force backward, it's slowing the flow down. Well, with these high velocities up here, the flow gets slowed down that much, and it's still going forward. But when you get down here really near the surface where the velocity is really low, that pressure force will slow that flow down so much that it'll actually start going backward. Because remember, we're moving along here, and so we're going region, 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 region. The pressure is always higher as it's going into it, so it's slowing and slowing and slowing the flow. So when you get down maybe to a point here, your boundary layer looks like this. Some of the really low velocity air near the surface has actually been pushed backward to the point where it's going backward. Just like if you're driving a car down the street at 1 mile an hour and somebody starts pushing backward on you, eventually the car will stop and then start going backward. Whereas if you're going 80 miles an hour, it takes a lot of force to slow it down, right? Same deal here. So the high velocity air still goes forward, but the low velocity air goes backward, and that is called flow separation, because it's kind of separated from the surface. It's going backward instead of forward, so it's not going with the flow, it's going against the flow. And this region builds as it goes down the airfoil until you get a huge region of flow. Let me draw my arrow further down here. You get a huge region of flow where the air is going backward and swirling around, And that's essentially called the wake behind the airfoil. And it causes a lot of drag, and you lose a lot of lift because the flow is not smooth over the airfoil. So in this region, the lift is lower than it would be if it wasn't separated, and the drag is higher. And if you're at a really high lift situation, right, we're generating lift, that means the pressure is really low, and so it has to go a lot more into the higher pressure region. So the lower the pressure is to start out, the more time the boundary layer spends in that pressure recovery region, and the more separation you get. Yeah? That's a different effect, but because typically you deploy the flaps, you don't get that much separation. They're designed not to. But it's the additional lift and the drag that you get from the lift. But if you deploy the flaps enough, you can cause this kind of separation, and then you get a lot of drag. So with the separation and stall is when this separated region covers most of the airfoil, then the wing has lost almost all of its lift, and that's why stall is bad. So if you keep tilting the wing up and up and up, you're producing more and more lift, but the pressure difference is so high that you get this stalled region all the way up here on the part of the wing that's producing most of the lift, and you lose most of the lift of the wing. So that's what causes stall. You have to be in a situation where you're producing a lot of lift, because then that pressure gradient, that pressure change is higher, and it has more time to reverse the flow. Okay, last thing about this. Remember turbulent versus laminar boundary layer profiles, what they look like. So I'm going to draw them separately now. So a laminar profile looks like that. And a turbulent profile looks like that. And the key feature here is that this has higher velocities near the surface, whereas this has lower velocities near the surface. So this is laminar. This is turbulent. So this has lower right? So if you go back to those pictures, laminar, the slope was up more like that, which produced less drag. Turbulent had those higher velocities near the surface. You get a lot more drag because there's higher velocities running into the surface roughness and slowing the thing down. Okay, now think about this. We've got a net force slowing this flow near the surface that leads to separation and stall. The boundary layer up here that has higher velocities near the surface is going to resist that slowing, right? Because it's got higher, bigger vectors here. So it takes a lot more net force backward to slow this and reverse the flow, whereas laminar has very small velocities near the surface. So even a small amount of pressure backward is going to slow that down and reverse the flow. So a turbulent boundary layer resists separation because of the higher flow near the surface. So now we're stuck in a quandary because laminar flow produces less drag, which is good. But turbulent flow resists separation. So what do? You design a completely laminar flow airfoil, and it's all great till you get close to stall, and then all of a sudden it stalls really fast, abruptly, and the whole wing stalls all at once, and you fall out of the sky. You build a turbulent flow airfoil, and it's got a lot of drag when you're trying to cruise, but when you come in for landing and you need a lot of lift, it's going to resist stall, so it's going to be stall resistant. So what you do as a designer is you pick the best of both worlds. Makes sense, right? That's what we all want to do. So what's done is that the wing is designed to be laminar over the surface here, and then deliberately on the surface you put some devices, you can put some roughness or other things here. They're essentially called a trip strip that changes the flow at that point to turbulent. And so you get laminar flow over a large part of the wing that gives you the low drag, so you're good there. But yet you get a turbulent boundary layer over the last fourth or so that then keeps this from separating, and it resists separation more. And you get less stall of the wing, and the whole wing doesn't stall at once. So that's how they get the best of both worlds. Wings are designed to trip. If they don't automatically trip due to their roughness, like the rivets and stuff in it, they will deliberately put something on here. When people build wind tunnel models to test their airplanes, the wind tunnel models are smaller. So that Reynolds number, remember it's RE and it's the dimension L or X. So the smaller scale models don't behave the same as a longer plate. And so what they'll deliberately do on the model is they'll put a roughness here, a trip strip, to trip the boundary layer at the point where it actually trips on the full-size airplane. So they test the correct boundary layer in the wind tunnel for their little model. So this is a lot of information, and this is about all that we do with boundary layers, but the key feature is, the key takeaways are, the roughness of the surface slows the flow down near the surface, so you get this boundary layer thing. Boundary layer means slower flow near the surface, and then when you get far enough away, it's just the normal free stream flow going by. We can predict how thick that is. We can predict the drag that we get from it. So we can calculate the total drag of our airplane. You have to add that drag to the normal lift pressure drag of the airfoil. And then we understand how different types of boundary layers cause separation or resist separation or stall. So you can understand why after people started building airplanes, they realized that this stuff was important because their wings started stalling and they had more drag than they thought they were going to get. Well, it was due to this skin friction and stuff like that. About 15 years ago, maybe 20 years ago, swimmers who swim through water, of course, started wanting swimsuits that would allow them to swim faster. And so what they want to do is reduce drag on their body. Let me turn the lights out, see if you can make this look better. They already did some fairly extreme things like shaving their heads or shaving their bodies to get the hairs off because they cause drag. Wore swim caps to keep the hair from flowing through the water. But then Speedo came up with various levels or designs of swimsuits where they incorporated boundary layer technology into the swimsuit to help the swimmer go faster, essentially reduce drag. And I'll zoom in on various parts of this. This is a full body suit, which was kind of the last iteration of swimsuits that they developed. There were some downsides to this, and I'll talk about it in a minute, but let me zoom in. All right, the first thing to notice is right here. Is it clear enough? You can see this kind of triangle-shaped patterns on this part of the suit. This is based after what they see in shark skins. The shark skin has little triangle-shaped patterns, and they've discovered that these patterns create eddies in the flow that reduce the drag. They prevent separation over the chest. So this reduces drag here as the flow comes over the top. Essentially think of the chest as the top of the airfoil. And then there's bumps here. They put those bumps there. Those are trip strips to trip the boundary layer from laminar, from this region, to turbulent to prevent separation over the chest. And then they go back to the shark skin pattern here. I don't know if you can see it very well. So these bumps are trip strips or transition strips to keep the boundary layer. It goes laminar, turbulent, and then it goes back to laminar as it goes through this region. And so that's one of the major features that they incorporated in this suit. And the suit all over has that shark skin pattern to reduce drag. Other features that are less boundary layer but are also important is the seams on the suit are designed to grip the water because the swimmer uses his arm to propel himself. So they actually wanted to create more drag as the arm pushed backward on the water. And the suit is compression, so it compresses the swimmer's muscles and keeps them from flapping around in the water and producing drag. So there's a lot of boundary layer and flow technology that went into this suit. And it's called the Fast Skin 2. And this is, they're talking about the scale pattern here. The seams were designed to grip the water. The fit was tight fit. The fabric had this special pattern built into it. But these guys did computational fluid dynamics, so they put the full tools of the aerospace industry and hydrodynamics into mapping pressure and velocity patterns over the body to help predict drag and reduce drag. And there's another picture of the flow over the person. And they tested these suits on people in a tank where they pushed water past the person and measured the drag. The downside to this suit, and if you watch Olympic swimming anymore, people don't wear this, it actually gave about a 5 or 6% reduction in drag, which led to faster times. But it was cumbersome because it took the swimmers a half hour to 45 minutes just to put the thing on because it fits so tight. And that caused all kinds of problems with delaying swim meets and swimmers getting in these suits and being ready to swim. But it was an application of flow, fluid, aerodynamics, and fluid dynamics and boundary layer theory that all led to this development. That's the end of chapter 4. I believe that's 4. And so we're going to go to 5 next, which starts talking about wings and airfoils and aerodynamic shapes. So if you want to read ahead, jump to that. The next thing and the last thing I'll do is hand out quizzes to the people that are here. I'll bring them back again on Friday for other people to collect.